Hello, my name is Michael Montiraju, and this is Physics 2212, Lab 4, Circuits. Here's an introduction to the lab. The purpose is to predict the behavior of circuits containing resistors in series and parallel circuits using the principle of current conservation. It's also to examine the behavior of capacitors and to measure current and voltage with a multimeter. Here are a preview of the results. The experimental RC that I got was 5.92 seconds, and the calculated RC was 6 seconds. And a major assumption we used in this lab is that resistance can be ignored from wires and ammeters when performing calculations. Okay, and so here's an introduction, continued, and some key ideas. So here is Kirchhoff's loop rule. The sum of all electric potential differences around a loop is zero. Kirchhoff's junction rule, or the node rule, and Ohm's law, which of course is one of the most fundamental electric laws. So here is part one, the experimental design. So this is a simple series circuit of two 1.5 volt batteries, two resistors, and two ammeters. Here are some predictions and calculations. I predicted that the first ammeter will equal the second ammeter based on the node rule, and I calculated the current based on Ohm's law, and it came to 0.204 amps. The observations the calculations are correct. Flipping the ammeter's nodes does nothing to change the number of amps displayed, and the voltmeter displays 3 volts just as expected from two 1.5 volt batteries. Part one is the data, and this is just continued, the data collected. The voltmeter was used to calculate the potential difference for each part around the circuit. The current always stays the same, 0.02 amps. And the following data was collected at points indicated on the figure below. So between B and A, between C and B, etc. These voltages added together equals a net 0.00 volts as predicted by the loop rule. And here's our resistance versus voltage graph, and that I used based on this data that I made based on that data. And here are some resistances for the two resistors, and then the wire and ammeter. Now here's part two, the experimental design and results. This is a circuit of one 9-volt battery, a 200 mF capacitor, and a 30 ohm light bulb. The light bulb starts off very bright, but as the current decreases, it becomes dimmer and dimmer. This is due to the capacitor losing charge. The voltage across the capacitor was measured using a voltmeter. The capacitor is discharged, and 20 seconds of the voltage data is collected. The voltage data is converted to the the ln delta V over delta V naught, or initial format, and plotted against time. The experimental RC is 5.92. So, and then if you calculate the actual RC, it's resistance times capacitance, so that's 30 ohms times 0.2 mF equals 6 seconds. So that is a little bit higher than what our experimental RC was. Here are some conclusions. So the PET simulation does a fairly accurate job at simulating a circuit. Some potential error is that the calculated resistant values are greater than the actual resistance of the resistors on the PET simulation. The ammeter precision is only to the hundredths place. What if you were doing this lab in real life and used an actual ammeter instead of an ideal simulated ammeter? What's the different about a real ammeter, and how would it have affected the circuits you hooked up to it? A real ammeter and wires have resistance. This affects the current flowing through the circuit. What if you were doing this lab in real life and used a real battery to charge a real capacitor with no resistor in the circuit? How quickly would our ideal model predict the capacitor to reach full charge? An ideal model predicts that the capacitor will reach full charge at a near instantaneous time. This would most likely not occur in real life. The capacitor and wires have a resistance that an ideal model would assume are zero. So the capacitor and wires do have a resistance in real life. We neglected them in this lab, but in real life they would not be zero. Of course, just to make it clear, this lab was the virtual lab, and not the actual, using the actual circuits. And that's that. Thank you.